And big, is it started? Good. Welcome, 3 people that are not here.
4 people.
And other weirdos on the internet watching.
4 people.
Reason?
Plus the 3 people are actually doing stuff.
So, yesterday we had a fun parametric test. I think I'm gonna grade it tonight. So hopefully I'll have the vector tomorrow. The homework was on cross products and vector creations of a line. Shall we do like one problem from each section?
No.
No? Yes. And then which one should we do? Let's do one. There was one, I think that was like a new thing that you've never seen before, right?
I got trapped in work the next time I go around in my
Are you going?
This is riveting video right now as we decide which one to do. Pick a problem.
1.
Do you want me to pan over to you right now?
Oh my god.
Here we go.
Hold on, for real.
1.
What do you got here? So page 321, you had to read and then no.
No, that was like one set of problems.
That was like, oh yeah.
Like this
Oh yeah. You had to do 2 problems, 19 and 22. The point of number 19 was to realize that the zero product property does not apply with cross products. Yeah? It is possible to have, actually explain why that's true. Like intuitively.
0x0 and 0y0.
If angle is 0, then 0.
Yeah.
Oh yeah, that's it.
Yeah. Or a
Wait.
angle of pi.
Those zeros in.
Parallel.
Oh, yes, duh.
Yeah.
Any 2 parallel vectors will have, though not the 0 vector themselves, will have a cross product which is the 0 vector.
Yeah.
Because it must have 0 magnitude. So that's pretty intuitive. And then 22 is another one of these like, yo, this is how sine and cosine work. Did you guys understand the point of Forster's explanation there?
Yep.
You should not try to find the angle between 2 vectors with the cross product. Intuitively, why? Unless you're like really careful. Yes?
Because it's the same thing as why you shouldn't use like the law of sines, it's like a safe angle because there are 2 angles less than 180 degrees that have the same sine.
That's right. Yeah, that's
and
right.
it'll always give you the acute angle.
Yeah, yes.
Wait, does this not apply with the cosine though, like a dot?
Right. Yeah, it's simply because when we're dealing with angles, and arc cosine goes from 0 to 180. I find this weird that I'm even making this graph, but I am right now. Ooh, weird. But the arc cosine is always going to output something between 0 and 180. So if you use if you want the angle between 2 vectors, then it's just arc cosine of the dot product over the magnitudes, but and that'll just like give you the right angle. But if you try, what's up?
So if you use the cross product though, don't you get like the other of the 2 angles? Because like there are 2 angles between.
Please pardon this interruption. At this time, all Bliss tutors should report to the Media Center for their monthly meeting. You should report during your respective lunch. So all Bliss tutors during 5th or 6th period lunch, please report to the Media Center. Thank you.
I guess it can go
The angle is up to you.
Yeah, the angle is obtuse, then it goes wrong.
between 2.
Because arc sine lives in 1 and 4, so.
Fix the camera. That's right. So if you have 2, thanks. Good. Yeah. So if you have 2 vectors, which are obtuse, I feel like I haven't fully thought this through. You have 2 vectors that are obtuse, and you take the
Cross product. And divide by the magnitude.
the cross product and divide by the magnitudes. Why is that wrong?
And then if you take
You'll
arc
get
sine and
the
magnitude,
magnitude.
Is there
Yes,
2
this
angles
one.
from 0 to 180?
you'll get this one. But is that just like wrong? Oh yeah, that is wrong.
Yes, that's
Yeah,
that's
yeah.
mine.
I mean, you can then find the other one, but you have to like know whether it's acute or.
That's right, that's right. Okay, sorry, I'm blanking for a second there. Yeah, if the correct answer to what is the angle between these two vectors is this angle, the obtuse. Yes.
I found two angles that didn't add up to 180. I probably did something wrong.
Yep. Okay, good. The next section was just like do a bunch of cross products. Looking at the person with the messiest handwriting in the whole world, trying to figure out what's going on. So I thought,
Questions clearly labeled.
yeah, that's true. The questions are clearly labeled.
Okay, number 22 was really good.
22 is good.
Yeah, because
No.
it's missing an equal sign.
22 is missing
It's
an
like-
equal sign. What are you talking about?
Vector B, X, I, something, I don't know. Unless I interpreted it wrong.
Oh.
Yeah, that's.
Inequalities, so I took
V,
equality.
line vector V, XI plus, shouldn't that be YJ? Is that what that's supposed to be?
It
Is
should,
this
no,
the Y?
it's saying the J coefficient is 1.
I think it's just the J one is just one. Like it's
Okay.
just one J.
Okay, whatever. So wait, hold on, no, okay.
Missing an equal sign.
We don't want to go over any of these, they're all fine, okay? Vector equation of a line, these, I thought one of these were like slightly cool, no?
No.
No.
No?
No.
Okay, wow, great. Alright, let's do a thing called, take out your packet called
Giant.
Giant Packet on Vectors. And there's a thing that I thought we could do kind of together that ties together some of the stuff that's going on. So if you turn to page 5, you will see us basically, okay, what we're about to do is do this whole find the equation of the line of intersection of two planes. And here is a problem, it's number 3. There are two options. Let's like do them the reverse way, because this is how we already learned it. So we have a plane. It's x plus 5y minus 2z equals -1. And the other plane is 3x minus 10y minus 5z equals 11. I want to say this was the last thing we did on Tuesday, was I asked you to find the equation of intersection of these two planes. And then you had a problem in homework like this, so you should be like good
I
at this,
feel like
right?
it was exactly the same problem.
Was it the exact same
I
problem?
mean, I remember like 3 and 2 were,
It was close.
it was close, yeah.
Okay, so anyway, can we quickly do this? How do you do this? How do you find the line of intersection of two planes? Yes?
You take the cross product of the normal vector.
Yeah, so everyone, let's like do that really fast on the bottom of page 5. Yeah, that's what we're getting to, Kevin. Okay, I will, I can get the planes back out again, but I don't feel like it. So yeah, if you take the normal vectors to the two planes and you take the cross product, we're in the bottom of page 5. Hayden,
Yeah, no, I'm just gonna do.
I'm just doing whatever, I feel like, cool. Okay. I got -45, -1, -25. Is that what you got?
Yeah.
Okay, cool. But because negatives are annoying, I'll just write this as the vector 45, 1, 25. Okay, that is the cross product of the normal vectors. So that means that that is the direction vector of the line of intersection. Agree?
Yeah.
Okay. All that remains, therefore, is to find a point which is on both planes, and the simplest thing to do is just set one of the variables equal to 0, it doesn't matter which one. We'll set z equal to 0, that gives me a system of two equations and two variables. So just like do this really quick. However you feel like. I don't know. I think I did that right. No. Did you get minus 14 over 25? Okay.
Did
There.
you cross the what, the normals? Or- Yeah.
Yeah, remember? Because that,
Yeah, I still remember now, okay.
right? Because you have the two planes. You have the two planes, and then you take their normal vectors. When you take their normal vectors and you take their cross product, you get a vector which is
Right.
perpendicular to both normals and thus parallel to the line of intersection. Having done that, this is the direction that that line points in. I just need a point. So in order, the simplest way to find a point is just set one of the variables equal to 0. This is like the burning lines of fire on the ground. Instead of a little system, 2x2 system, I solve it algebra 1 style. I think I'm done. The vector equation of this line is x, y, z equals the point 9/5, comma, negative 14 25ths, comma 0. Make some noise if I'm doing something wrong, but I feel like I'm not. 45, 125. Okay, congratulations, you found the line of intersection of the two planes. Alternatively, we may do something that at first seems totally different, but is in fact like the same thing. And actually, this is one of the benefits of being in functions, because in the pre-calc kids, they do a whole unit on vectors in pre-calc B. And like the whole summer goes by. Then in pre-calc C, they do a unit on like systems of equations and matrices, and they're sort of like totally separate from each other. Whereas I think the connections are more interesting between these two. So another way to solve this same problem, take this plane, x plus 5y minus 2z equals negative 1, and 3x minus 10y minus 5z equals 11. And now, just treat these things as like solving the system, right? This is, what I want is the line of intersection. In other words, I want all the points which are on this plane and also on this plane. That's just what the line of intersection is. So I'm looking for all ordered triples which make this equation true and also make this equation true. In other words, I'm just looking for all the points which are solutions to the system. So, doing the same, and I made some space in the packet on the next page for you to do this whole problem over again in the other way. The other way is just treat this like a system of equations and just go. Have you done problems like this before?
Well,
Kind of.
yeah, because like we've done problems where there's a third equation that turns out to be 0 equals 0.
Right.
And that you just basically add that equation if you really wanted to.
Yup. That is a good way of thinking about it. He says, if it makes you feel better to throw on an extra equation of all zeros, go for it, but that really doesn't solve anything. So I converted it into a matrix for simplicity, and now just do the Gaussian elimination algorithm on this matrix. Go.
Is that like the augmented matrix or some crap like for like
Exactly.
what's it called?
Mm-hmm. Augmented matrix. Some people put little colons, but I don't. I get this. Is that what you got? Okay, I could stop here, or I could do one more thing. I'm gonna do one more thing. This would be fine, but it actually works out kind of prettier if you do the full Gauss-Jordan. And how do you do Gauss-Jordan when you have just two lines? What's the only other spot I can turn into a zero if I really, really want to?
The -2. Where the -2 is right now.
What's up?
Wherever the -2 is right now, I think.
No, I actually don't have the power to force that to be a 2 because,
I mean, you.
well, okay, I guess I do actually. That's sort of not the normal way to do
I
it.
guess do it with the 5.
Yeah, you can kill the 5, that's true,
Yeah.
you could do either. Yeah.
The -2
Yeah.
seems nicer to do.
Yeah, but no, I think the problem is if you try to make the -2 a 0,
Oh,
I feel like that's actually not gonna work,
But then you
right?
would have the z be a free parameter if you keep both of them there or something.
Right, but if I try to multiply this row by like 2 or something, no, I guess that would work. Anyway, I'm gonna kill the 5. So how do I kill the 5? Well, first I'm gonna make that -25 a 1. So let's just do that. So I'm gonna divide row 2 by -25. -1, -14, 25. And then we're just starting to look a little bit familiar actually. And then I can use that 1 to kill that 5 by replacing row 1 with -5 row 2 plus row 1. Bob? 0. No, this is a little bit annoying, this part. But not so bad, actually. Yeah. 0, 1. Okay, is that what you got?
Yes.
Okay, and now we're sort of done. There's no more that we can do to this. Now we've done the full Gauss-Jordan elimination. Okay, what does all this crap mean? Well, it means, again, that I have sort of these two planes, and the intersection of these two planes, of course it's going to be a line, and it's the same line as the line of intersection of these two planes. But now this has been fully reduced, how can I write out all the points which satisfy this system? We just do it with a free parameter. So let that free parameter z be represented by the letter A. And if z is A, then what's y? What's y? Can you guys just do this in your head? Because this second equation is really saying 0x plus 1y minus 1/25 z equals -14/5. So y is just
25, or A of 5.
1/25. Yep. Cool. And then z, or x, and here's like now the benefit of having put in the effort to make that 0. I don't actually have to do any work now, right? What's x? X is just, move that over.
9A over 5.
Yep. 9/5 A plus 9/5. Okay. So, Gaussian elimination tells us that all of the points which satisfy both these planes are any point of the form 9/5 A plus 9/5, comma 1/25 A minus 14/25. Are we still in frame, Hayden? Supposed to be like monitoring that constantly. Comma A.
Yeah.
Good. Okay, now you could just leave it like that, but of course, what's the relation between these two? This is where the magic happens. Yeah, this is kind of cool, right? Because now this ordered triple, I know you might be talking about something else, Kevin and Sav, I don't think you guys should be saying the same thing. Seems like that. What are you doing over there?
Probably something like math competition related. It has nothing to do with what we're doing now.
Okay, we can rewrite this as, split this up into two pieces. Split this up into the things that have an A in them and the things that don't. So this is really like A times 9/5, 1/25, 1 plus the leftover, which is 9/5, comma, negative 14/25, comma, 0.
Or you could
It's
just
almost
leave it
like
as
too
is,
cool.
then also.
It's almost too cool, he says. Yeah. So what is this? This is just a vector equation of the line, right? This is really just saying, yo, this is the line x comma y comma z, where I have a point, 9/5, negative 14/25, 0, plus a t, it really doesn't matter, 9/5, 1/25, 1.
So, you know, everything that you ever want to know about.
Oh, I think I must have messed up somewhere. No.
No, this is right, this is
Did I
right.
reverse it? No, I didn't.
That's right,
It's
that's
good.
right,
That's right.
Yeah, and
It's divided.
exactly. So note that we got the exact same thing. These are two different ways of solving and two different ways of thinking about the same problem. Here we take two planes, we take their normals, we know things about the normals, we know things about the cross product, we find the direction vector, and we find a point. Here, we just be like, dude, the intersection of two planes is just a set of all points which satisfy both planes. So let's just find the set of all points which satisfy both planes. You just do Gaussian elimination, and then you arrive at the exact same thing. Of course, these are the same line because these direction vectors are scalar multiples of each other. And if you multiply this one by 25, you can see it's the same thing. Yes?
Why can't you just leave it as like this?
You could also just leave it like this. But this further shows the connection between the sort of purely algebraic way of looking at it as just a system of equations and the geometric way of looking at it as a vector equation of line. All right, how are you feeling about that? Good, that was way too slow.
With the vector.
New thing.
So
Turn the camera.
three people
And we're getting close to like what life is all about here. I want to talk about a concept of. Actually, I changed my mind. Let's do it over here. Leave the camera. I want to talk about. Why laughing? I want to talk about a concept of linear algebra, and that concept is called linear independence. Super important, and something that will come up over and over again. So we're giving a little intro to this now. All right. Well, duh. Every vector, like u, for example, can be written in the form b times the I vector plus c times the j vector. That's just our normal way of writing it. Well, what I'm now going to introduce you to is this thing called a column vector. So what is a column vector? It's just a vector, but it's just written differently. It's written like in a column. So, and you can use parentheses, you can use brackets, it's like everyone does their own thing. So, the vector I, well what is the vector I? In component form, it's just like 1, 0, right?
Yeah.
But instead of writing 1, 0, we just read it like that. We kind of did this already with, we did this. Did we just Anyway, here it is right now. Is everyone okay with this notation? I feel like it came up one more time, but I can't remember. Okay, so we say, here comes the vocab, every 2D vector can be expressed as a linear combination of the vectors 1, 0 and 0, 1. Alright, so what is a linear combination? This is kind of a shorthand for a sum of scalar multiples of. And it's sort of awkward to always say that. Multiples of. So this is just expressing the totally obvious fact that every 2D vector can be expressed as a sum of scalar multiples of these two vectors. Luke, get it?
Yeah.
Duh, what's not to get?
Wait, of what?
Example of 1, 0 and 0, 1.
I think you have an extra O.
I don't think I do. Well, maybe I do.
Yeah.
Better?
Yeah.
Let's do this.
Yeah.
Okay. So, take an example. The vector 7, 11. How can we express the vector 7, 11 as a linear combination of 1, 0, 0, 1? Yeah. I just take 7 of those 1 zeros and 11 of those 0 1s. Okay. There is an obvious graphical interpretation of what it is we are doing. We are following these vectors in a certain kind of like order or whatever, right? So imagine that here we have the thingy, and here we're going up here. We're trying to get to the point 7, 11. How do we get there? Well, we just go like over 1 and 3, 4, 5, 6, 7. Then we hop on the up train. And we ride the up train 11 times. Follow? Say yes.
Where each
Okay.
train only moves once, like that's like every
Yep.
single-
Okay.
Yeah.
Question. New question. Is the vector 7, 11 a linear combination of, for example, vectors 1, 2, and 3, 1?
Okay, you just check the system resolution.
So, first of all, let's think about what this even means. Is it possible to add up certain multiples of this vector and this vector such that the sum of those multiples ends up at 7, 11? Answer?
Yes.
Of course, he says. Shall we just like do it? I don't know. Or should we just try to draw it and see what happens?
Totes.
Like, did you say totes?
Yeah, it is.
Whoa. Totes, he says. Yeah, what does the vector 1, 2 look like? Well, over 1, up 2, boom, there it is. Let's call that maybe like vector u or something like that. Then we have vector 0, 1, 2, 3, boom, boom. You can call that like vector v. So you can think of these as like trains. Can I ride certain numbers of u and v trains, possibly fractional amounts of them, possibly negative them, to make it to the vector 7? It feels like yeah, right?
Yeah.
Yeah, in fact I could even probably like, depending on how good my picture is, and it's not good, I could probably even estimate this as like, I'm gonna ride maybe u like a bunch of times, so I don't know, like 2, 3,
Wait, including
4,
Flash, can't you do any
maybe like
vectors?
4.5, and then maybe I need to write v like almost 1-ish. Does that look about right? Kind of ballpark?
Fractions, you can do any.
Okay, could you, Vic, stop talking? And second of all, now that we feel like this is doable, can you please find the scalar multiples of the vectors u and v needed to go? Just get it in your head. Whoa. So basically, I'm trying to solve the equation. Hey now, is there a scalar times this 1, 2 vector, and another scalar times this 3, 1 vector, which when added together is vector 7, 11?
System of equations.
It's just a system of equations. In fact, what we have written here is a vector equation. This vector equation in 2 variables can be translated naturally into a system of equations. Is everyone cool with this? This is like pretty intuitive. Yeah. And now you can solve this system however you want. I'll just do it the fast way. Try to do it correctly, because that's always good. Good job. And A is 26 fifths.
Yeah.
Okay, it's even kind of like what we predicted, right? Here is what this tells me. This tells me that if I ride the U train 26, a little bit more than 5, yeah, 26 fifth times, then I will get, and then I ride the V train 3/5 times, I'm going to get to the vector 7. Okay, cool. So yeah, this is appropriate because like, you know, the whole metro shut down yesterday, and that's why no one bought my both Wizards tickets last night. It was really annoying.
Wait, why did that
They just shut down the entire metro for 24 hours, unprecedented.
I thought it was
It's
29.
pretty pathetic.
Wait, did you see some of the photos though of like
No,
the
I haven't had a chance.
cables being cracked and stuff?
Yeah.
Like that?
Yeah.
It's pretty bad.
I think if you shut down any very important institution and then look at it very carefully for 24 hours, you're gonna find some bad things.
I heard they're shutting down all planes tomorrow.
What?
Yeah, all planes.
Okay. Another weird hated joke I don't ever fully understand. All right. Good. So, where is this all building towards? What is this concept of linear dependence and linear independence? Well, here it is. Oh, by the way, Vic was saying something important, which is, yo, duh, can't I just always get to any point whatsoever with any two-dimensional vectors?
Yes.
Yeah, it seems like I can, right? Yeah, it seems like you're gonna pretty much just get
Distinct, you
anywhere.
have to specify the distinct.
What?
Can't be parallel.
Non-scalar multiple.
They have to be not parallel vectors, right? Yeah. And what we say, the phrase that we say is that, yes, span, 1, 2, and 3, 1, span the plane. Which is just a way of saying with combinations of those two vectors you can get anywhere you want. Okay, more. So, here's what we say. A set of vectors is linearly dependent. This is the vocab here. If one of them can be expressed as a linear combination of the others. One of them can be expressed and if this is not possible, we say the vectors are linearly independent. Not possible.
So you need exactly 2 parallel
Independent. Okay, yeah, we're gonna see how this all plays out in various dimensions. Okay, let's do an example. These examples are kind of pretty silly and easy. First example, take the vector 1, 3. Oh, let's just do the case we just, no, let's take it as a case. 1, 3, and 2, 6. Okay, call this vectors, call the vector 1, 3 u, and call the vector 2, 6 v. Is this set of vectors linearly dependent or linearly independent?
Dependent.
Yeah, a set of vectors is linearly dependent if one of them can be expressed as a linear combination of the others. Okay, well duh, dude, v is just 2u. So, of course, these two are dependent. So this set is linearly dependent. Follow? Okay. But on the other hand, example number 2, oops, gave it away. Vectors 1, 2, and 3, 1, as we've just seen, if this is u and this is v, can I express one of these vectors as a linear combination of the other one?
No.
Like, no, duh. So this is linearly independent. Does everyone see the general gist?